Ooh, sorry, I didn't mean for you all to hear that. It's just that when I get excited, I bark like a dog. And can you blame me? What's more exciting than the opportunity to jump right back into our quadratic relationships from Units 8 and 9, this time in the form of quadratic functions. Next on the chopping block for our families of functions, just like with equations, if we up our exponent by 1, it moves us from the land of linear functions to quadratic ones. As we know from Unit 8, these functions can come in a variety of forms. We've encountered 3 of them. Take a look back at your notes and remind me what they are. Go! And stop. Well, first of all, we know we can always encounter a quadratic function, just like any other function, in standard form. Now for standard form, the only change that we make is that y is getting replaced with f of x, our dependent variable notation, but the ax squared plus bx plus c on the other side of my equal sign is unchanged. After standard form, we learned that if we factored it, we could arrive at the intercept form of our parabola. Once again, the notation is exactly the same, except we swap out y for that dependent variable f of x, but we've still got that GCF A times some quantity x minus p times some quantity x minus q, right, our factored form. Now we call it intercept form because those values p and q, they tell us something about our graph. Remind me, what is it that they tell me? 5 seconds, go. 4, 3, 2, 1. Well, it's in the name. If it's intercept form, these are going to be my intercepts, specifically the places where we cross the x-axis, which you may remember we can also call, especially when we're working with functions, the zeros of our graph, and this happens at those values of p and q. And last but not least, after intercept form, we talked extensively about graphing parabolas in vertex form. Just like intercept form, in the name here, there's something really important told to us about our graph. Its general form, once again, swaps out y for f of x, but on the other side, we've still got that a times our quantity x minus h squared plus k. And again, these values of h and k are really important for us. They give us, unsurprisingly, the vertex of our parabola at the coordinate h, comma, k. Lovely. So once again, just like linear equations, I know how to define a quadratic function. Now I want to be able to figure out when I've got one on my hands. Let's start with equations. So I've got 3 equations down below for functions. I want to figure out which of them are quadratic. Well, what is the criteria that we put on our quadratics? And once you've got that criteria, try your hand at the 3 below. Which of them represents a quadratic function? Give it a shot. Okay. Once again, by definition, an expression or an equation, or in this case, a function, is going to be quadratic if I see that all of my variable terms are of a degree of 2 or less, which we'll write as less than or equal to 2, right? As long as the biggest exponent that I see is 2, I'm usually good. Of these 3 functions below, I want to figure out which ones are quadratic. Well, f of x equals 2x. Again, we've established f of x is really just y, so that guy has a degree of 1. 2x, even though it's attached to a 2, has an invisible exponent of 1. This guy is not quadratic. It is, in fact, linear. But for number 2 here, I've got 7 minus x squared plus 3x. Even though it's not explicitly in standard form, we can see that our greatest exponent is that 2 on our x. This guy is quadratic. And for h of x is equal to negative 5, quantity x plus 2 times x minus 1, you might be deceived because both of these x's have an invisible exponent of 1. But if I were to met-wet out, we would see that this guy is indeed going to be quadratic, right? This would become negative 5. X times x would be x squared. 2 times x is 2x. X times negative 1 is negative x. Put them together, we should get positive x. 2 times negative 1 at the back is negative 2. Now we see that we do indeed have that exponent of 2, we are a quadratic function. Fantastic. Let's move on now to graphs. If I give you a visual, remember that the graph of every quadratic equation looks the same, which means the graph of every quadratic function should look the same as well. What do I know about the shape that each picture should take? And then once you've got it, tell me which of the ones below meet that criteria. Give it a shot. And stop. Well, we know that any quadratic equation, and therefore any quadratic function, will take the shape of a parabola. So as long as my graph is parabolic, then I know that I should be a function. So for A, this is a parabola. It's concave up. So this guy makes us happy. Now for B, even though it does have what appears to be a vertex, and we will in fact describe it as a vertex when we talk about this type of function soon enough, it is not quite a parabola, right? It does not have a nice curve, so even though it kind of looks like a parabola, it's not enough to say this is a quadratic function. Now for C, I would agree that this guy is quadratic, but it can't possibly be a function. Why would C not be a function even though it's quadratic? 5 seconds, go. 4, 3, 2, 1. Well, it fails the vertical line test. If I were to draw this vertical line here we see it intersects the graph at 2 points. Even though it's quadratic, it cannot be a function. And last but not least for D, we've got a parabola. It's concave down, that's fine. It passes the vertical line test. This guy is indeed a quadratic function. And last but not least, just like with linear equations, there's something interesting to say about what happens when we represent the points on our graph using a table. So again, I've given you an equation here for q of x squared minus 3. I want you to evaluate q of 0 through 7. As you do, keep an eye out for patterns, right? We know something about linear functions. I want to see what happens when it's quadratic instead. Give it a shot. Tell me what you notice. Go. Alrighty. Well, if I plug in 0 for x here, I just need to evaluate. Q of 0 would become 0 squared minus 3, which is just negative 3. Plugging in 1, 1 squared is 1. 1 minus 3 is negative 2. For 2, this would become 4, and 4 minus 3 is 1. For 3, this would become 9 minus 3, which is 6. For 4, it would become 16 minus 3. 16 minus 3 is 13. For 5, that would become 25 minus 3. 25 minus 3 we know is 22. For 6, that would become 36 minus 3. 36 minus 3 is 33. And for 7, 49 minus 3 is 46. So here, we can observe the same thing for x. Notice that every time that I go to the right 1 row, I add 1 to increase my value of x. But if I take the same strategy as I was doing with my linear functions, well, if I try to take the first difference, to get from negative 3 to negative 2, I add 1. But to get from negative 2 to 1, I don't add 1 anymore, I add 3. But hopefully you'll notice, if you keep finding these differences, that the number which we increase by is increasing at a constant rate. Here it's increasing by 2 each time. So even though the first difference is not constant, if I were to find the differences of the differences, we'll see that we add in that second layer the same number every time. We are going to call this then not the first difference, but the second difference. And if our second difference is constant, then we will have on our hands a quadratic function. Give it a shot for the 3 tables below. Can you tell me which of these 3 are quadratic? Go. Alrighty. For our first one here, notice that x every time is going up by 1. So if it's quadratic, that means the second difference must be constant. Well, let's see what happens with the first difference first. To get from 6 to 1, I need to subtract 5. To get from 1 to -4, I need to subtract 5. Same thing to get from -4 to -9. This guy is not quadratic. We should know well this is what type of function? 5, 4, 3, 2, 1. Well, just like we know from last class, this would be a representation of a linear function. Now let's take a look at B. So I've got -2 to 0, 0 to 2, 2 to 4. Every time, I hope you can see, I'm adding 2 to get from one number to the next. Well, to get from -4 to -1, I need to add 3. From 1 to 4, or -1 to 4, sorry, I add 5. And from 4 to 11, we add 7. If we take our second difference here, you will once again see that we're increasing at a constant rate. Our second difference is constant. This guy is a quadratic function. And last but not least, over here, from -6 to -5, right, I need to add 1. Same thing to get from -5 to -4, and from -4 to -3. Now let's find our first difference. If it's constant, then we know it's linear. If it's not constant, it might be quadratic. Now to get from 11 to 1, I need to subtract 10. To get from 1 to -13, right, I need to subtract 14. And to get from -13 to -31, I need to subtract 18. Now, once again, I'm going to check my constant difference here for the second layer. Well, -10 to -14, that would be subtracting 4. And to get from -14 to -18, I once again subtract 4. Look at that. We have a constant second difference. This is a quadratic function as well. Beautiful. Now, just like with linear functions, a couple of things, some potpourri that we want to be able to do. The first of which is identifying the transformations specifically from vertex form. Take a look back at your notes from Unit 8, right? What do each of these guys, A, H, and K, tell me from a transformational perspective? How does it change the way that my graph looks or where it lives on the coordinate plane? Take a couple minutes, do some research, and come back to me. Go, go! Alrighty. Well, this variable A up at the front, it can give me either a vertical stretch or a vertical compression. I often abbreviate vertical again as V and compression as comp. It is also potentially responsible for a reflection over the x-axis. This guy H in the middle is going to give us our horizontal translation, which I often abbreviate as H trans. And for K here, this is going to be our vertical translation. It's going to move us up and down. Take what you know here. For J of X, K of X, and M of X below, can you tell me what each of the numbers in each spot is doing to change my graph from that parent graph, which we'll now call the parent function, f of x equals x squared? 2 minutes. Try it out. Alrighty. Well, for the first one thing that I might want to do, remember your superpower as a mathematician is to make things look the way that you want it to look. Here to make it more obviously in vertex form, I'm just going to switch the order of my signs so that the x squared stuff comes before the 1. Now it should be obvious what's happening from a transformations perspective. Well, the minus sign in front, this is going to cause a reflection over the x-axis, so we'll be concave down. And this +1 here outside of the square is going to move me up by 1 unit. For k of x is equal to 3 times the quantity x plus 2 squared. Again, only 2 things happening here. No rearranging that I need to do. This 3 in front is greater than 1, so it is going to cause a vertical stretch by a factor of 3. And this +2 inside of the square, remember it always does inside of the square the opposite of what you expect. You would think addition would move you to the right. It's actually going to move you to the left by 2 units. And last but not least, for m of x equals -4/7 x minus 5, quantity squared minus 8. Well, this minus sign out in the front, this is going to cause my graph to reflect over the x-axis. The 4/7, which I think independently from the minus sign, is less than 1. So this is going to cause a vertical compression by 4/7. This -5 inside of the square, again, it does the opposite of what you expect. You think subtraction moves you left. It's actually going to move you to the right by 5. And last but not least, this -8 at the back, outside of the parentheses, it does what you expect. We're going down 8 units. And for our last trick of the night, I want to also be able, just like linear functions, to find the equation of a quadratic function. So let's take this guy over here. N of 1 equals -6, and the vertex appears at 3, 4. I want to write this in vertex form. So remind me, what is the vertex form? And take a look back at your notes, right? What are the steps that I can take to reverse engineer the equation of the function with these characteristics? Go, go! Alrighty. Well, here I know that my function is going to be using n as its rule. So instead of f of x, we're just going to call this function n of x. And we know that our vertex form is a times the quantity x minus h squared plus k. Once again, we know our vertex is 3, 4, which means that h is 3 and 4 is k. Same thing as our linear function. If I have something in function notation like this, this is really a point in disguise. Well, if the input 1 gets me the output -6, then x is 1 and y is -6. So in my equation over here, that means that this 1 is going to take the place of x, while -6 here is going to be my output value y, which we're writing in function notation as n of x. All I need to do now is slot into place. So using what I know, we've got n of x, which we've identified as -6. We've got a, which we need to solve for. We've got x, which is 1, minus h, which is 3, all inside of our square, plus that value of k, which is 4. Next up, all I need to do is get a. So the first thing that I might do is simplify inside of these parentheses. There are lots of choices that you can make. I'll make this one first. Well, 1 minus 3 is -2, and -2 squared is +4. So I've now got -6 equals 4a plus 4. Well, to solve for a, let me begin by subtracting 4 from both sides. -6 minus 4 is -10. So if -10 is equal to 4a, I just need to divide both sides by 4 to get that a is equal to -10/4, which reduces to 5/2. Now that I've got a, all I need to do is substitute into that function equation above. Well, I need my n of x to be in function notation. I know now that a is equal to -5/2. X needs to stay in order to use that function notation, minus our h value, which we identified as 3, quantity squared, plus k, which is 4. Next up, our warm-up for tomorrow's class will be this guy. I've got something now in intercept form that I want to find. I can use these criteria to do it. If you're feeling bold, if you're feeling brave, try it out on your own so that we're ready to go for tomorrow. But if not, who cares? Give yourself the break if you'd like. It makes no difference to me. Have a lovely night. Take care, be well. I'll see you when I see you. Goodbye. Bark, 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 bark.